The last big part of this unit also deals with solutions, but now it's solutions where acids and bases are dissolved in water. So we are going to learn how the pH changes with this, what are acids, what are bases, how to recognize them, and what properties they have. So in short, acids, and that's Bronsted-Lowry definition, are proton donors. I'll explain it in a second what that means. And bases, they are proton acceptors. They capture hydrogen ion. So, and this is also repeated here. So acids, they are proton donors, and they produce what we are going to learn is called hydronium ion. And if you measure the concentration of this hydronium ion, that's what pH is. And then we're going to learn about the pH and how to interpret it. And then acids can be strong or they can be weak, and that they're also going to affect the pH. Strong acids are going to change pH a lot. Weak acids are going to change it just somewhat. Now bases, they are proton acceptors, and they often, not always, but often they give hydroxide ion in water. And again, they can be strong and weak. So now, acids are unique substances because they are covalent compounds, but as soon as you mix them with water, they begin to act as ionic compounds. So the hydrogen that normally is a nonmetal and shares electrons with other nonmetals, when you put it in water, this bond between hydrogen and the other nonmetals is becoming so weak that it's actually kind of breaks, except it's not really, it doesn't break the bond. The electron is going to be retained with other nonmetals, and instead hydrogens that used to have, so think about the hydrogen atom, it has one electron and one proton. The electron will stay with the rest of the nonmetals. Only proton is going to be released into the solution. So we learned that ionic compounds form when electrons transfer from metal to nonmetal usually, right? And in case of hydrogen, it only has one electron. So if it begins to act as a metal and if it gives away electron, then what's left? Only proton. So we can use interchangeably the word proton and hydrogen ion. So when hydrogen becomes an ion, it's the same thing as just having a proton. So it doesn't have anything else. Because hydrogen, the most common isotope of hydrogen, does not have neutrons. Some of the isotopes do, but the most common one doesn't. So this is the only element that can exist without neutrons, and that's why we call it proton donor or proton acceptor. So acids are substances that donate this proton or form hydrogen ion in aqueous solutions. And bases are going to be substances, other substances that are present there that are going to capture it. So hydrochloric acid, for example, right? So if you think that it has hydrogen and chloride, they're sharing, that would be correct. But when you mix it with water, look what happens. Chlorine steals this electron that used to belong to hydrogen, and now it obtains a -1 charge. The same way if it was taking it from sodium or from lithium or from calcium or from other metal, it would just take it, right? So it takes this electron. And what's left here instead of hydrogen is hydrogen ion, or we also can say a proton. That's what's left, and that's what's being released. So when we say proton donor, it releases this proton into the solution, into the water. Hydrogen bromide, the same thing. Hydrogen iodide, same thing. Now for nitric acid, right, same idea. So it's going to release hydrogen ion, and then the NO3 is a polyatomic ion that's going to take away this electron. That used to be, this electron together with hydrogen ion together made hydrogen atom. Now, acids can be strong and they can be weak. You have to just memorize and know by heart the 3 strong acids. 3 strong acids are hydrochloric, nitric, and sulfuric. Those three are strong acids. So when it's asked you for hydrochloric acid, is it strong or weak? You say strong. And I will explain what that means. Hydrobromic is weak. Hydroiodic, weak. Nitric, strong. And both, like I said, for now, just do it with me, and then I'll explain how it affects the properties. So the anion that is being formed, right, would be the species that steals this electron from hydrogen. And that becomes chloride, bromide, iodide, and nitrate. So if we continue, sulfuric acid is another strong acid, and it produces sulfate ion. Carbonic acid is weak. Acetic acid is weak. Phosphoric acid is weak. So the only strong ones are sulfuric, hydrochloric, and nitric. The rest of them are going to be weak acids. The difference is that strong acids dissociate completely, 100%. That means that they produce a lot of ions, and they are strong electrolytes. Weak acids, right here, and there's more than this, it's just examples. They are weak electrolytes because only some of the molecules are going to release this proton, not all of them. So it doesn't happen to every molecule, just some of them are going to release proton into the solution. Others will still stay with covalent bond to hydrogen. So if you look at it right here, you'll see that strong acid dissociates 100%, right? So every single molecule that you put there is going to produce proton and some kind of anion. Versus weak acid, it's going to, so look at it. So most of it will stay the same, right? So most of it will stay intact, but some will produce hydrogen ion and anion. So that's the difference. So right here, lots of ions versus here, few ions. And you can see another representation over here. So in other words, lots of hydrogen ions because it's, every single molecule. If you add the same amount of hydrochloric acid and carbonic acid to two different beakers, you'll have much more protons in a beaker with hydrochloric acid than you do where you added carbonic acid. So we already are familiar with reactions of dissociation when we were showing how ionic compounds break down into ions. Same idea as here, except now we're looking at acid, and hydrogen in this case is going to act as a metal, and it's also going to produce an ion. So you can see over here where my sulfuric acid, it broke into two hydrogen ions and one sulfate, right? And that's two hydrogen ions because I started out with two atoms of hydrogen. Remember that this -2 for sulfate, that's because this two electrons combined with those two protons would make two hydrogen atoms together. Now, another one is potassium hydroxide. Hydroxide groups often that means that it's a base. And if you recall just a while ago, I told you that bases, they take the proton. So this hydroxide group is able to combine with a proton, right? So it's a base. Not all bases have hydroxide group, but this is a very common one. And it will break down into potassium ion and hydroxide ion, right? Now let's do some concept checking. How can we recognize an acid by looking at the formula? Well, normally think about what's the same about all of those acids. You can see that they all have hydrogen connected to some kind of anion, right? So if you imagine that instead of hydrogen you had a metal, that would be definitely an ionic compound. But here we have hydrogen. How can we recognize a base? Well, in this class, just know that it's going to have a hydroxide ion. It's not always there, but for this class, that's going to be enough. So you'll have a hydroxide ion. Why do we call hydrogen ion a proton? Because we have proton in the center, in the that makes up a nucleus, and then we have one electron that orbits around. If you take away an electron, there is nothing else left except proton. So hydrogen ion has only one proton and nothing else. The next question, monoprotic, diprotic, and this should say triprotic acids. So what does it mean? You think about the name, monoprotic. So it's acid that can release only one proton. Diprotic, that's acid that can release two. And triprotic is acid that can release three protons. So for example, HBr is going to be monoprotic. H2CO3 is a diprotic, and H3PO4, that would be a triprotic because of the number of hydrogens that it has, and it is directly proportional to how many protons are going to be released or can be released. Now, number 5 gives the names of some common bases and determines their weak or strong. So how can you determine if it's weak or strong? The bases that are made of metals in group 1 and 2, so metals in group 1A and 2A produce strong bases. And metals metals or anything else that's not in group 1A or 2A would be weak. So this one is going to be sodium hydroxide. And that's going to be strong because sodium is in the group number 1. Strong base and weak base is the same idea as with acid. Strong bases dissociate completely. So when you put them in water, every single molecule ionic compound that you put is going to break down into individual ions, versus weak is going to somewhat break down, not completely. So barium hydroxide is the next one. It's also going to be strong because barium is in the group number 2A. So barium hydroxide, that's going to be strong. The next one is ammonium hydroxide. And since ammonium is a positively charged polyatomic ion, but it's not a metal from group 1A or 2A, that's going to be weak. Hydroxide, that's going to be weak. And the last one is potassium hydroxide. That's also strong because potassium is the same as sodium hydroxide, is in the group number 1. Potassium hydroxide. And that would be strong. Question number 6. If I have aqueous solution of HCl, which is a strong acid, what species do I have in the solution? So not only I'm going to have water, but if I put HCl there, it's going to produce hydrogen ions and chloride ions, right? If I have, and that would be strong acid, so 100% of my HCl will break down. If I have aqueous solution of hydrofluoric acid, which is weak acid, what do I have there? I'm going to have water. I'm going to have hydrofluoric acid, and I'm going to also have some hydrofluoric acid that will break down into protons and fluoride ion. But I have now this 4 species versus before I had this. So only some of my hydrogen fluoride dissociated. If I have solution of nitric acid, what's going to be there? It's a strong acid. So every single molecule is going to break down. So it's going to break down into hydrogen ion and nitrate ion, right? So we are going to have this species there. And it's going to be also 100% of my nitric acid that dissociates. Now, number 9, now it's weak acid, which is hydrocyanic acid. So if you put it in water, we have water. We have hydrocyanic acid that mostly will stay as is. And then we have some that's going to break into hydrogen ion and cyanide ion. Next question. What is the difference in the extent of ionization or dissociation, in other words, of strong versus weak acid? Strong dissociates completely, and weak dissociates only partially. Next question, if I put 1 mole of strong acid and 1 mole of weak acid into 2 different beakers, do I have the same hydrogen ion concentration? So concentration is usually indicated by square brackets. Do I have the same hydrogen ion concentration in both beakers? The answer would be no. And the reason why is because if I'm putting, this is my 1 mole, so I'm putting the same amount of molecules, right? Mole is how many molecules. I'm putting the same number of molecules of strong and weak acid. However, my strong one is going to produce a lot, right? For every molecule of strong acid, I'm going to produce hydrogen ion, a lot of hydrogen ion, versus weak, only some of them are going to break down, so few hydrogen ions is going to be produced, so much more for strong acid. Interesting thing is that water is a weak acid. And let me explain. So it actually can break down. So if you think about it, HOH instead of H2O, it can break down into hydrogen ion and hydroxide ion. So very, very few molecules. It's a very weak acid. Very few molecules are going to do it. In fact, there's going to be only approximately 4 out of 1 billion water molecules that are going to do it. The rest, practically 4 billion, practically 1 billion of them, right? They are going to stay as H2Os. They stay intact. But 4 out of 1 billion, billion is 10 to the 9th, are going to break down to produce this. You can also see that not only it produces hydrogen ion, but it also produces hydroxide ion. And I told you that hydroxide ions, that's normally a basis. So water has a very unique property. It can act as an acid and it can act as a base. And that's really cool. But calls this property self-ionization or auto-ionization of water. So in 1 liter, only 1 out of 555 million, which is approximately 500 million water molecules, dissociate into ions. And this is what I was showing you before. The interesting fact that's written here is that if you could randomly remove and examine 10 particles per second from a liter of water, liter is really not a lot. It would take 2 years working nonstop to find 1 ion of hydrogen ion. So it's very, very small concentration, to say the least. In fact, we know exactly what the concentration is going to be. If you look below, it says that it's going to be 10 to the negative 7 moles per liter, so it's molarity. So this is the concentration. So when we break it down, it's going to produce 10 to the negative 7 of hydrogen ion and 10 to the negative 7 of hydroxide ion. Now, the interesting thing is that as soon as hydrogen ion is released into water, it's not going to just float around as a proton. This proton is captured immediately by other water molecules, forming what we know as hydronium ion. So technically, when we say that there is a hydrogen ion that's being released, well, yes, it's released hydrogen ion, but it never exists in the solution because it immediately forms hydronium ion. And without water, that would not be even possible, the release and everything, because remember, acids, they only release this proton in aqueous solution. So you have plenty of water molecules around, and one of them is going to capture and form a hydronium ion. So you can see this in more details over here. So this lone pair right here and lone pair over here. So one of them is going to capture. And if you imagine that if you take one proton, that's proton, and you take just one electron, together they'll make hydrogen atom. And that's this hydrogen atom. Now, what's left on oxygen is one electron, and now my hydrogen atom has one electron. So they are going to share and form a covalent bond. So basically, it's oxygen sort of like gave its electron to hydrogen, and then they shared them again. So they formed the bond. So now we have positively charged hydronium ion. Why is it positively charged? Because you just added a proton without adding any additional electrons. So it's a hydronium ion. Now we can summarize those two reactions, reaction 1 and reaction 2, in what's called self-ionization of water. We have two water molecules, and one of them, let's say this one, gives proton to another one. So it's going to act as an acid, right? So it's going to give away proton. And another one is going to act as a base, because the definition of a base, it accepts proton. So look what happened. My base that took the proton, it became hydronium ion. And what's left of my acid, if it gave proton, what's left is negatively charged hydroxide ion that's left in its place. So you are going to, as I said, produce those two species, hydronium ion and hydroxide ion. Sometimes it can be interchangeably referred to as hydrogen ion, because it is understood that hydronium ion cannot form unless hydrogen ion is being released. So they're not the same thing, but the physical meaning is kind of the same in the solution. So in water, hydrogen ion exists as hydronium ion. So please remember this. And their concentration you also have to memorize. The concentration of both is going to be equal, because for every one hydronium ion, you produce one hydroxide ion, and it's 10 to the negative 7 molar. The out-ionization of water has two consequences for aqueous solution. First one is that if you change the concentration of hydronium ion, it causes this change of hydroxide ion, and it is an inverse change. So when one increases, another one decreases. So the higher the concentration of hydronium ion, the lower the concentration of hydroxide ion will become. The higher the concentration of hydroxide ion, that would lead to decreased concentration of hydronium ion. So they will stay, they interrelated. And the other consequence is that all of the ions are present in all aqueous systems. However, when you have acidic solution, you have more hydronium ion. And think about it, makes sense, because the more acid you are adding to the solution, the more hydrogen ions are going to be released, and the higher the concentration of hydronium ion. In neutral solution, you have equal amounts, and that's why pure water is considered neutral, because you have self-ionization of water, but it's equal concentration of hydronium and hydroxide ions that are being produced. And in basic solution, you have more hydroxide ions and you have hydronium ion. Because dealing with concentrations such small as 10 to the negative 7 or 10 to the negative 2 or 10 to the negative 14 and so on is inconvenient, scientists come up with a way of doing it. They decided to use a negative logarithm of this concentration. So if you take negative log of the concentration of hydronium ion, that would be pH. So when we refer to pH, we really are talking about how many hydronium ions you have in the solution. So in the neutral solution, the concentration of hydronium ion in a neutral solution is 10 to the negative 7 molar. If you take negative log of this number, it's going to be opposite in sign to the exponent. So the pH of neutral solution is 7. If you increase concentration of hydronium ions, I need you to think about it. If it goes up, then it's going to be So for example, if I have 10 to the negative third, why is it higher concentration? Because negative third is greater than negative 7, right? And the negative numbers, the closer you are to the 0 on the number line, the more positive, the greater the number. So negative 3 is actually greater concentration. So that's what, and if you take negative log, the pH is going to be equal 3. So numerically, my pH decreased, but concentration increased. So that's kind of the opposite, right? So, and I'll reiterate that in a second more, just so that you remember better. But let's look at concept checking and see how we can apply. What is a hydronium ion? Hydronium ion is this. What is a hydroxide ion? Is this. Please remember and don't confuse them. Shows the reaction of autoionization of water. So we have two water molecules. One is going to give proton, another one is going to take proton. So you are going to form two ions, and do not forget the charges. That's super important, because one gave just the proton, not just hydrogen. It didn't give up hydrogen atom. It gave up hydrogen ion, which is a proton. And the electron stayed where it was before. The pure water, the pH of pure water is 7. The concentration of hydroxide ion in pure water is 10 to the negative 7. So don't confuse pH and concentration. They are related, but they're not the same. The concentration of hydrogen ion in pure water is also 10 to the negative 7, because in pure water we have equal concentration of those, and that's going to be 10 to the negative 7 molar. What is the range of pH scale? Traditionally, we say 10 to the 14, 0 to the 14, but it actually could be 10 to the 15. However, this is what we are going to focus mostly on. Number 7, what ions are present in neutral solution? If it is neutral, then you have both. You have hydrogen ion and hydroxide ion, and they are going to be in equal concentration. That's, that's what makes it neutral. What ions are present in basic solution? Well, you still have both, but you are going to have more hydroxide ions. What ions are present in acidic solution? It's still going to be both, but now you have more hydrogen ions. If I have high concentration of hydrogen ion in the solution, would the pH likely to be 2 or 9? Think about it. So if I have high concentration of this, and I'm choosing between 10 to the negative 2 and 10 to the negative 9, because that's what those pHs are, right? That's my concentration. Which one is a greater concentration? And that would be 10 to the negative 2, because again, in negative numbers, 10 to the negative 2 is greater than 10 to the negative 9. So if I have high concentration of hydrogen ions, that means I'm going to have high concentration of hydronium ions, which out of those two is going to be 10 to the negative 2, and the pH at this concentration equals 2. If I have low concentration of hydroxide ions, so be careful, it can be tricky. So if you have low concentration of hydroxide ion in the solution, so I have hydroxide ion, and it says that it's a low concentration. If my concentration of hydroxide ion is low, that means, so it's, I'll show it like this. That means that at the same time, the concentration of hydronium ion is high, because they're related. If one decreases, another one increases. And if I have the concentration of hydronium ion high, pH only shows me hydronium ion. It doesn't show me hydroxide ion. So it's 10 to the negative 4 versus 10 to the negative 10. That would be the right answer, because if it's high, then it has to be pH 4. What ions are present in a greater amount in neutral solution? No, they are going to be, there's no greater amount. They are going to be equal amounts, because that's what neutral means, that they balance each other and neutralize each other. What ions are present in a greater amount in a basic solution? Well, in this case, it's going to be hydroxide ion. What ions are present in a greater amount in acidic solution? That's going to be hydrogen ion. Which acid 147 or 10, or which pH 147 or 10 is most acidic? Well, at pH 1, you have the greater concentration of hydronium ions than you do at pH 10. So that would be pH 1. One way to remember is to think this way. If I have low concentration of hydronium ion, like small concentration, I'm going to have big pH. If I have big concentration of hydronium ion, I'm going to have small pH, right? So if I have pH 1, that means that I have a lot of hydronium ions. So that's going to be acidic. Which pH, 147 or 10, is most basic? Well, if it's basic, that means I have small amount of hydronium ions. Then my pH has to be big. That would be 10. In number 17, it says a notation in square brackets, H3O plus means concentration of hydronium ion. So in brackets, we have concentrations, and this is hydronium ion. And if we look at the options that we give, moles of hydronium ion, concentration of hydronium ion, mass in grams of hydronium ion, or concentration of water, the answer is going to be B. And why is it not A? Yes, it is. It's still, measured in moles, but it's moles specifically in 1 liter. It's not just moles, because I can have moles in 5 liters, in, 20 milliliters. That's not the same, as molarity always tells you how many moles are in 1 liter. So it's a concentration. Show how pH scale mathematically related to concentration of hydronium ion. pH is a negative log of hydronium ion concentration. So if you have pH scale starting from 0, then 7, and then 14, then the concentration of hydronium ion at pH 0 is actually 10 to the 0, which is much greater than concentration of hydronium ion at pH 14, which is 10 to the negative 14. So that's your concentration of hydronium ion. In number 19, if I put 1 mole of strong acid and 1 mole of weak acid into 2 different beakers, do I have the same pH in both beakers? No, I don't, because pH is related to the hydronium ion concentration, right? And strong acid produces a lot of hydrogen ions, so high concentration of hydrogen ions that change into high concentration of hydronium ions, right? This is because hydronium ions form when hydrogen ions are captured by water, versus weak acid produces small amount of hydronium ions. So the pH, the greater your concentration of hydronium ions, the lower the pH, lower pH. And so this is going to have lower pH than this. This is going to be higher pH. They both are going to be acidic. It's still going to be acidic, so it's still going to be on the side. So if you look 0, 7, and 14, they both are going to end up somewhere between 0 and 7. But strong acid is going to be closer to the 0 than the weak acid. Now remember I told you that the concentration of hydrogen ions and hydroxide ions are inversely related. This is going to be handy in this problem. The concentration of hydroxide ions is given to you, and that's 10 to the negative 4 molar. You need to find concentration of hydronium ion. Remember that concentration of hydroxide ion and hydronium ion in a neutral solution is equal, and it's 10 to the negative 7 and 10 to the negative 7. And if I change one, I'm inversely changing the other one. So if my concentration of hydronium ion is 10 to the negative 4, which I know because of this, right? So it's 10 to the negative 4. Then the difference between them, this negative 3, 10 to the negative 3, has to be added. That's the difference. That has to be added here. And and that's going to be 10 to the negative 10, right? So, and at 10 to the negative 10, pH is going to be 10. So this is my answer in terms of concentration. That's if I need to convert it to the pH. Let's do one more problem like this. So if my concentration of hydroxide ion is 10 to the negative 9, I need to find the concentration of hydrogen ion. So remember again that we started out with 10 to the negative 7 for hydroxide ion and 10 to the negative 7 for hydronium ion when it was a neutral solution. Now my concentration changed to become 10 to the negative 9. So it decreased by 10 to the negative 2, by 2 powers. That means that this has to increase by 2 powers, right? So that would be, increase is going to be negative 5. So my answer is going to be 10 to the negative 5. What is the pH at 10 to the negative 4 concentration of hydronium ion? Well, negative log of 10 to the negative 4 equals 4. And the next question, the pH of 1 by 10 to the negative 9, we can drop the 1, so 10 to the negative 1 is going to be negative log at 10 to the negative 9 equals 9, and that's my pH.